When objects collide with each other, so let's say that this object 1 is moving to the right, and maybe object 2 is at rest. They're on this flat surface here. When 1 hits 2, they will touch each other, just like anything else would touch each other, even if we just put them right next to each other. So 1 and 2 will touch each other, and in this moment, the forces acting on 1 would be a force from object 2 on 1, so 2 on 1. There's also the earth pulling down on this object, and there's the surface of the earth, the surface of the table pushing up on it. And then object 2 over here, when object 1 hits object 2 there, object 1 will apply a force, the force of 1 on 2, and there'll also be a gravitational force and a normal force from the surface. Now what I want to highlight here is this action-reaction pair. So these two forces, this force and this force, are the action-reaction pair. Newton's third law tells us that for every force there is an equal but opposite directed force between two bodies. In this case, we have our two bodies. We had our object 1 here, and we had our object 2 there. And so notice that the direction of the force on 1 and the force on 2 are opposite directions. And those forces will be equal to each other. So if we use Newton's second law, and that the net force is equal to ma, then we can look at what's happening here and say that our force, the net force, is equal to mass. Now, acceleration is defined as the change in velocity over a change in time, or final velocity minus initial velocity over final time minus initial time. And most of the time, our initial time is 0. And so we'll just have our t on the bottom there. And so if I go back over here and substitute that, I'll have our final velocity minus our initial velocity over time. So during the collision, this net force causes the mass to have a change in velocity, and I'm going to distribute the mass here, so I'll have mass times final velocity and mass times initial velocity, all divided by the time. Now, if I look at the force applied, the net force, times the time, so I'm just going to multiply the time over, I'll have v final minus v initial. So like in the video, when the egg struck the wall, so there was an egg, and the egg was moving towards the wall. The wall was a rigid wall. When the egg hit the wall did not move, and the egg was splat. Now, when the same size egg was thrown, but it was thrown at a sheet, and so the sheet was connected here, and as the egg struck the sheet was able to bend and give, and let the egg fall and roll down. And this kept the egg from breaking. So, while the initial velocity of our egg was the same in both cases, and the mass of our egg was the same in both cases, mass and our initial velocity, and we wanted to stop the egg, and in this case, the final velocity was 0, and in this case, our final velocity was also 0. So what was different about each one of those scenarios was that the force and time combination was different for each. So the time that the egg went from moving to not moving was a very short amount of time when it hit the wall. So we had a time that was very small. But over here, the time that the egg had to slow down was much bigger. I'm going to call it T big over here because the sheet moved with the egg. So the quantity that we get when we multiply mass times velocity is called momentum. The symbol we use for momentum is a lowercase p. So P is equal to mv. I jokingly call this momentum, just to remind myself that the symbol that we use is P. We use M for mass and V for velocity and T for time. There weren't a lot of M's left over to use for momentum. So the letter P was used because of a Latin root word for this momentum or perpetual motion. So that means that when we have our net force applied to this object that's causing it to slow down, multiplied by the time, we'll get a final momentum minus an initial momentum. Now, anytime we have a final value minus an initial value, that is a change. Remember, the delta symbol represents change. So our net force times time is equal to our change in momentum. Now, this force times time quantity is often referred to as the impulse. So the impulse is equal to the change in momentum. So impulse is equal to change in momentum. Now, if we think about what's happening in this terms of a force, so if we have force and we look at time, now the egg colliding with the wall, there was a very large force over a very short amount of time, and our egg stopped. The egg thrown at the sheet had a long time to stop. And so the force time graphs look different. Now, mathematically, I could consider what's going on here and say, well, the area under this curve here, this purple area I'm drawing here, would have to be equal to this pink area here. So I can get the same area for these different shapes, but because the force is lower here under the pink curve, then a longer time allows us to spread out, or allows a smaller force to cause the same change in momentum or the same impulse. So the area under our force time graph, the area is the impulse. And the impulse is also the change in momentum. And this is a concept we use all the time. So a trampoline is fun because the springs and tarp allow you to bounce up and down, and the tarp will flex as you collide with it, and that flexing keeps you from becoming injured. That's why jumping from a high cliff, you'll want to jump into water, or a stunt actor will have some sort of airbag set up here, or there might even be a trampoline. So increasing the time that a force acts on an object will allow the object to slow down at a reasonable rate so that bones aren't crushed and your soft tissues don't get damaged. Now, mathematically finding the area under this kind of curve is pretty difficult in terms of algebra. We could use calculus to determine it, but we're not going to use calculus in this course. So if we simplify the force, we could simplify it and just make a triangle. And then the area under the triangle is just 1/2 base time height. And that is a much easier calculation. Now, sometimes you have a force that's applied, and that force is nice and constant. And so then our equation is even easier, just base times height for the area here. And that gives us the change in momentum, or the impulse. So impulse is the same thing as change in momentum. So let's look at that one more time. So our impulse is equal to our net force times time, which is also the change in momentum. Now let's talk about our unit here. If the force is measured in newtons and time is measured in seconds, then impulse is measured in Newton seconds. I'm not saying newtons per second, I'm saying newtons times seconds. Now, change in momentum is mass times change in velocity, or mass times final velocity minus mass times initial velocity. And in this case, mass is in kilograms and velocity is in meters per second. So if impulse is our change in momentum, then these two units must be equal to each other. Now I can check that because remember, a newton is a kilogram times a meter per second squared. And then we multiply that by a second here, and we'll get kilogram meters per second. And if you look, this is now the same as that. So a newton times a second is equivalent to a kilogram meter per second. Now, since force is a vector and velocity is a vector, that means that impulse and momentum are also vectors. So remember, vectors have magnitude and direction. So they both have a number, and magnitude tells me how big. So that's like the number or the size. And it has a direction. So is it positive or negative, or up or down? Those direction words are important. And so then we must also calculate our change in momentum, being very careful about the directions of our forces and our velocities.